Augies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Today's question comes from longtime patron Roy Gertig. He asks, we talk about current in the house coming in on the black and returning on the white for alternating current. We feed an antenna and we see the representation of current across the dipole. However, where is the return leg making this alternating current? Okay, he's N0RG. Roy, let's take a look at this. In a house, okay, you got your meter and you've got your current coming in and you've got 3 wires. One wire is actually connected to ground. Okay, the other wire is called the neutral, and it's the white wire. And it is connected to this at a single location only, and that is in the panel. Okay, and then this is the hot. Now, the way it works out, there's 2 hots, but we won't worry about that because we're not going to worry about 220 volt circuits, just 110. So now these go through breakers, and a breaker is a switch, which is normally closed, okay, normally closed. And then these come to their load, and I'll put a resistance here to indicate the load. Now, if you've got fans and stuff in your house, you've also got some, this is R, this is L, it's reactance, okay. And it's actually the reactive at 60 hertz. Or 50 hertz if you're in Europe, or in a lot of other places around the world. You know, it used to be in the United States, there was 50 hertz and other places 60 hertz. And then, I mean, even in cities, there'd be differences here. And then everybody went to 60 in the United States. That is not true abroad. So, now this is AC current. So if you look at one instant, the electrons are going this way, okay? The next instant, or 1/60th of a second later, it's going that way, all right? Going back and forth. The electrons don't really get anywhere, but then we're talking purely in terms of DC. It goes this way, then it goes this way, and then it goes this way. But we don't talk of it that way. We talk of the power being pushed to the load, and that goes one way over here, okay? Let's take a look at something. Let's assume that the voltage, here's the voltage, okay? And then the current is going to be right here also. Now, the power that's going in this direction is the current times the voltage. So the power equals EI. Now, positive times a positive is positive, right? Well, look what happens right there. Now we have a negative times a negative, which is positive, right? So the power is positive here. Is positive. The power is positive here. The power is always positive, and the direction of the power is what we're interested in. What the power company sells us is energy, all right, which is power times time. So when we talk about power, we're talking kilowatts, or watts. When we're talking about energy, it's watts times time, or watt hours. We measure that in hours, watt hours, and that is what we actually pay for, the watt hours, okay? Now, I'm not going to talk about the inductive load in there. What the inductive load does very briefly is it causes the current to be slightly delayed, and so you end up with a short piece in here where the power is actually negative, because you got a positive current and a negative voltage. You end up with minus power, and so the power becomes power equals the volts times the amps, and we call it volt amps. You've probably heard this before. And then there's something called the power factor, which is between 0 and 1. The idea is we want the power factor to be as close to 1 as possible. If it's less than 1, that means there's an out of phaseness in here, and that comes from the inductive loads in our house. Most households have net inductive loads. The power factor is slightly less than 1. We don't pay for instantaneous power. We pay for the net power times the time. And the utility has to fix this because it causes overloads on their lines. But now, what we've seen here, we can talk in terms of power going in one direction. This is the ground here. It's ground. It's neutral. This is ground. This, by the way, is the 3-wire ground, or the green wire. Okay. It's connected to ground at one place. Neutral is connected to ground at one place. Now, the way that GFI circuits work, ground fault interrupter, is they have a little coil here. They are measuring the current on both sides here. Okay. And if those differ, it'll trip, because that means that some of the current is coming back through the ground. So the two are, you've got a dangerous situation somewhere in that current is leaking. That last couple parts about the power factor and the GFIs is extraneous information, but fun nonetheless. Now let's look at a radio frequency transmitter. It has an oscillator, okay? And then a power amplifier. A power amplifier, and this could be 5 watts out, 100 watts out, 1.5 kilowatts out, whatever. But let's take a dipole, okay? Now the dipole, classic dipole, is joined in the middle, and this is your transmission line, okay? And this is also grounded. So this right here is the equivalent of the hot, if you will, and this is the equivalent of the return. So you have this dipole here, but let's look again, like we did with that. In which direction does the power go? The power goes this way, okay? This is power, sometimes called forward power. Okay, and then negative power, or return power, goes this way. And this is what creates the SWR. Because if you take the forward power over the forward plus the return, this gives you the reflection coefficient, which is the capital letter omega from Greek letters. It was like an F without the little thing there. This is the return coefficient. And if you take 1 plus the magnitude of the return coefficient divided by 1 minus the magnitude of the return coefficient, I put the F on there, I'm not supposed to do that. That is the SWR, the standing wave ratio. Now, so power is going in one direction, although you do get some reflected power. Return power or reflected power. Now, think of this again in terms of AC. You've got a circuit over which the power flows, but the forward power only goes in one direction. And it is split. I'm talking the power now. Now the current in the antenna goes back and forth. But the important thing, it is the current that actually causes the radiation, not the voltage. The voltage is high at the ends. Again, AC or RF voltage is highest at the ends, lowest in the middle. The current, I'll just put an I there, is highest in the middle and lowest at the ends, whereas the voltage goes the other way. That is AC, okay? Now, the two curves cannot be sine waves out of phase with each other, because if there are, there is zero power. If we take a wave like this, and we have another wave that is 90 degrees out of phase. So this is the voltage. Here is the current. Okay. So that's positive power. This is positive power. Now note here, this is positive while this is negative. So that's negative. Okay. So where do we come up with our other negative? And here it is negative. So we have positive, positive, negative, negative. And the amounts are equal. So the power, the total power, is 0. That's because the power factor here equals 0. The power factor equals 0, which gives us, you have to know the number of watts in the presence of a power factor. It is the voltage times the current times the cosine of the power factor. Okay. And in here, you've got a 90-degree phase angle. Cosine of 90 degrees is 0. 0 times whatever is 0. So if you have out of phase on here, there is no power. So therefore, the voltage and the current are not sine waves. They can't be, or there wouldn't be any power radiated. Now, if you think of this in terms of RF, remember a transmission line carries RF. So think of it, where's the power going? We're not going to worry about where the electrons are, just where is the power? You are feeding power along a transmission line, power, and it is going to an antenna. Now, I'm going to throw something at you that's going to blow your mind. In much of ham radio, we want an antenna that's 50 ohms. And we want a transmission line that's 50 ohms. What does this mean? E equals IR, or R equals E over I. So the resistance or impedance in this case, which would be Z, is the ratio of voltage to current. The ratio of voltage to current. We call this 50 ohm cable because if you've got a 50 ohm load and power is only going in one direction. Okay, we call this 50 ohm cable because everywhere along this at RF, the RF current divided into the RF voltage, the ratio of the voltage to the current, is 50. Okay, so if you got 1 amp of current, you got 50 volts. All right, ratio of the voltage to the current. Now, we generally like to transmit more or less power than that. Okay, it's 50 ohms. Now, I want you to think of something funny. What about air? And for that matter, vacuum. Air has electromagnetic waves, right? And you've got the electromagnetic wave traveling this way. You've got the, that's the electric wave. And then the magnetic wave is perpendicular to that, okay? And it's traveling also at the speed of light. They're in phase. If you look end on, you've got the electric up here and the magnetic down here, which is often the B field. Don't ask me why they use B when we're talking electromagnetic waves, but they do. Okay, these can actually be measured with a field strength meter and so on. But this is how they are in air. What is the ratio between E and the magnetic part? We'll just call it B here for the magnetic part, because this is voltage and this is current. The B is actually measured in amps. Now, there's a little difference. Volts per meter and amps per meter. So if you have, you're measuring two distances, the E field at a meter apart, the voltage difference across those points. I mean, we're talking thin air here, but conceptually, that's the volts. The amps is the current. Why? Because in a coil, It is the amps, or I, going through here that creates the magnetic field. And same for voltage, except that's the voltage across the resistance. What is the ratio of the volts per meter, so that's volts per meter, times amps per meter, Notice, they're both per meter, per meter, per meter. In the units, we can just cancel these out. They cancel each other in this equation. So we have volts over current. And what is the ratio, meaning the impedance of free space? 377 ohms. Okay, 377 ohms. So that's an omega. That's not a very good omega, but that's a good omega. Okay? 377 ohms is E over B. So if you want to think of purely at RF, okay, you have, and we'll just put this down as we've got 50 ohms in our transmission line, and we've got 377 ohms in air or free space. This travels at the speed of light. This travels somewhat slower than the speed of light through this. What we have here is, you can think of the antenna transforming the impedance of our radio wave from 50 ohms to 377 ohms. Isn't that interesting? We are seeing the antenna as the transformer that takes us from 50 ohms inside the transmission line to 377 ohms in free space. Okay, that's an interesting way of thinking of an antenna. Now, it doesn't matter if this is 600 ohms transmission line, or we're going to have some sort of a transformer there or something. But still, we're transforming what's in the transmission line to what's in free space. This is in free space, okay? It's a very interesting way of looking at it. Here we are thinking only of RF. RF goes this way. It needs either a transmission line here, which has a positive and a neutral if it's unbalanced, and then there is no transmission line here, except it's either air or free space, okay? This impedance here, you can measure the voltage, you can measure the current, okay? You can measure them with a field strength meter. And you see these field strength meters. This is a field strength meter right here. Now there is a RF, and this is milliwatts per meter squared, okay? Now if I were to turn this on, okay, it's in CW, so I'm going to push this. You don't see much here. We're transmitting, see? And again, we're interested in power, because that's the power going forward. Now you can see there's hardly any reflected power right there. Most of the power goes forward. Okay, now let's see what happens if we see it here. I don't know if we'll see it here. Now we're not seeing it here because the antenna's outside, but look, you can see a little bit. Let's try it. Let's peek. Okay, this is right here magnetic. This is volts per meter. And you see what happens when I turn this on. We'll use just this. Okay, this takes a little while. I'm actually overloading it so much, okay, that it's up here. But this thing measures the volts per meter, and it can measure microteslas. Look at that. It's coming up. That's the microteslas. What's between here and here? Air. Okay? So we're measuring that, the volts per meter. By the way, I have several of these electromagnetic force or That's what we're talking about here, meters, and none of them read alike. So you can't trust the actual amount. You just get sort of a, yeah, there's something going on here. So I hope that I've answered the question. First, if you have a coax and it's got an outer shield, okay, the return is along the outer shield in terms of AC, and this one is the hot. All right, now you can also do a open feed line where these are balanced and go both ways. When this one goes this way, here, this way, here, or if you want to do it in terms of thinking in terms of AC, what you've got is a hot plus and a hot minus, and there's a, think of this as a virtual ground in between. Okay, this is easier to visualize what's going on. All right, so let's take a look at what we've learned here. We did this first DC, we see, you know, the individual wires, but we've learned that when you get to RF, the old notions of power going like this, not power, but electrons going like this, that power goes in one direction, from the source to the load. Okay, now we can take that in the same way on an antenna with RF being AC, that the power goes from the source to the load. But if there's an impedance mismatch, it will reflect a little bit of that power. It's almost impossible to get a perfect match, which would be a 1-to-1 SWR. It's always a little higher than that, like 1.1 or 1.2 to SWR. Our transceivers are built for that. Okay, so we see the power going in one direction, and then it hits the antenna. Now, antenna physics is fascinating, okay, but the net result is that the RF power in the transmission line is converted to RF power in the electromagnetic field. The ratio of the current to the voltage to the current inside a transmission line is its characteristic impedance, usually 50 ohms. Although sometimes we might use a 75 ohm cable or something. 50 ohms is standard practice, okay? So 50 ohms to a device that converts that to the 377 ohms, that's voltage divided by the current, of free space. The antenna is the one that does that translation for us. So what happens in an antenna with individual electrons? The way the antenna works, it's the current that creates electric waves, okay? We don't much care about the voltage. The current creates the electric waves, but a changing electric field creates a changing magnetic field. And that is how, if you plot down there the way these things move, you get a little electric field that starts to move away from the antenna. Okay, and that creates a magnetic field in air. Okay, so now you have an electromagnetic field, and the ratio between the voltage, which is you're taking that current and creating a changing voltage, okay, which creates a changing magnetic field, and the ratio of those volts per meter and amps per meter is the characteristic impedance of the big transmission line, if you want to think about it, of 377 ohms. So we went from tech to general to extra to engineering level talking about these things, okay? There's just so much cool stuff to antenna physics. You've got to get the book from the league and read it on antenna physics. It can blow your mind. And yes, to do it properly, you need vector calculus and all that. But we can just think in terms of general principles. So there you have it. All yours. Until we next meet, 73.